with a little review problem as we lead to the rest of our chapter. So when hydrochloric acid is poured over potassium sulfide, 42.9 milliliters of hydrogen sulfide gas is produced at a pressure of 752 torr and 25.8 degrees Celsius. Write an equation for the gas evolution reaction and determine how much potassium sulfide in grams reacted. So this question tells you actually to write an equation, but even if you didn't, it's good to write an equation when you have multiple substances reacting together, because you would need your mole ratio to use the information of one substance to solve for the information of another. So this is a gas evolution reaction. It even tells us we have hydrochloric acid and it reacts with potassium sulfide. Well, this is a gas evolution reaction because we know that H2S is a gas that forms, and then we have our remaining aqueous substance. Now, we have to make sure this equation is balanced. I would need a 2 here and a 2 here. Awesome. So then let's see what I'm given here. So when hydrochloric acid is poured over potassium sulfide, 42.9 milliliters of hydrogen sulfide gas is produced. So I have 42.9 milliliters of this gas. It has a pressure of 752 torr and a temperature of 25.8 degrees Celsius. Write an equation, we already did that, and then determine how much potassium sulfide in grams reacted. So I want the mass of this. Okay, well, how do I figure that out? If I ever want to go from this substance to this substance, I need moles. I always need to use my mole ratio. So therefore, I have to use all the information I'm given from hydrogen sulfide gas to get moles. Since I have one of each of the variables, I can use my ideal gas and isolate for moles. Now, remember our constant you always have, it's 0.08206 liters atmospheres mole Kelvin. Now, you can convert your constant if you wanted to. I personally like to convert everything to match the units of my constant. So pressure would have to be in atmospheres. So 750 torr times 1 atmosphere over 760 times 0.0429 liters, just dividing it by 1,000, divided by R, 0.08206 liters atmospheres mole Kelvin, and then 25.8 plus 273.15 Kelvin. And then this gives you 0.00173 moles of hydrogen sulfide gas. Awesome. So now you have your moles and you can use your mole ratio. What is your mole ratio between potassium sulfide and hydrogen sulfide? It is a 1-to-1 ratio. So I would like you to always show your work for it. And then you want mass. So since now I am in moles of potassium sulfide, how can I get the mass of potassium sulfide? Molar mass. We know that molar mass can always help convert from moles and grams of the same exact substance. So you find your molar mass, you sum it up together. Where do you find molar mass? Periodic table, you always have that available for you. And 110.262 is what I got for it. Over 1 mole. Moles cancel and you're left with grams. And you get 0.191 grams of potassium sulfide. Now we have the grams, we have the substance. How many significant figures do we want? 3, good. And then you are done. Awesome. So now what we're going to talk about is moving on a little bit into a theory and then real gases, kind of straying away from the idea of ideal gases. So the kinetic molecular theory helps explain some of the behavior of gases and then helps further explain those laws that we talked about. So we've discussed that we know how all these laws kind of describe when things are held constant, how different variables act. And this theory is the simplest model to explain the behavior of gases. It's a gas that is modeled as a collection of particles. So either molecules or atoms, depending on the gas, that's in constant motion. And because particles and atoms of a gas aren't constantly in motion, certain little points of the theory have been generated. So in this model, we say that the size of a particle is negligibly small, meaning that we don't care about the size of the particle specifically. We're thinking of assuming that the particles themselves occupy negligible volume, even though they have mass. This is because under normal pressures, the space between atoms or molecules in a gas is very large, because you have to think about the fact that they're bouncing away from one another. So the space between them is really big, but themselves are very, very small. We don't really need to know about how big or large they are, since the distance between them is so big. Another point is that the average kinetic energy of a particle is proportional to the temperature in kelvins. Now, average kinetic energy, what is average kinetic energy? It is energy of motion. So how does that relate? So if I increase the temperature and I have a sealed container so my particles can escape, what would happen to them? Well, the motion of atoms or molecules in a gas is due to thermal energy, the energy that's in the atoms and the molecules to move. So that distributes itself among the particles in a gas. So at any given moment, some particles are moving faster than others. There's a distribution of velocities. Not necessarily if you increase the temperature, every single gas particle is going to move the same. Now, every gas particle could have a different mass, and that's something we'll talk about in just a little bit. But they're going to be affected, but they have a distribution of velocities. But the higher the temperature, the faster the overall motion of these particles will be, and therefore the greater the average kinetic energy. So we know that they're directly proportional when we're looking at particles. One more thing that we look at is the collision of one particle with another. So we're thinking that they could collide, or they could collide with the walls of the container they're in, the particles. It's very elastic, or completely elastic, I should say. So when two particles collide, they may exchange energy, but there's no overall loss of energy. Any kinetic energy lost by one particle is gained by the other. So this was in that billiard ball example in the earlier lectures. So when one ball collides with another, that kinetic energy is transferred to the other ball. There's no energy ever lost. So the particles have no stickiness, and they do not deform by the collision. An encounter between two particles in kinetic molecular theory is more like the collision between two billiard balls than the collision between two lumps of clay. So think of two billiard balls. When you hit one and it hits the other ball, right? It gives it that energy to then have the other ball move, but it doesn't deform. Whereas two pieces of clay, if you then stick them together, they're going to change the way that they look because they deformed. So 3 major points. The size of the particles are negligible. The gas particles form elastic collisions with themselves and the walls of their container. And the average kinetic energy of a particle is proportional to the temperature. So gas particles are in constant motion. You're never going to have a container full of gases that's just sitting there. They're always in motion. And this constant motion causes the particles to forcefully strike the walls of their containers. And since they're constantly forcefully striking the walls of their container, they have a constant pressure. The gas particles have sufficient energy then to overcome the attractive forces and therefore fill up their containers. They take shape in the volume of the container. So according to kinetic molecular theory, a gas is a collection of particles in constant motion. The motion results in collisions between the particles and the surfaces around them. And each particle collides with the surface. It exerts a force upon that surface. So this is a way that kinetic molecular theory helps explain pressure. We know pressure is equal to force over area. And we know that from Newton's second law, force is associated with an individual collision. And we think that force is mass times acceleration. And that acceleration is due to the collisions. So this is how kinetic molecular theory helps explain the nature of pressure. We know that each particle collides with the surface and exerts a force upon that surface. And the result of many particles in a gas sample exerting a force on the surfaces around them will be the constant pressure. So then if we think of Boyle's law, we already know that Boyle's law is the relationship between pressure and volume. So if I decrease my volume, as you can see here, my particles have a lot less space to maneuver around and my pressure increases. But why does that happen? So we know that for a constant number of particles at a constant temperature, the volume of a gas is inversely proportional to its pressure. According to kinetic molecular theory, if we decrease the volume of a gas, we force the gas particles to occupy a smaller space. Now, this will increase my pressure. But this can only occur as long as the temperature remains the same, the number of collisions with the surrounding surfaces must necessarily increase, which then will increase the pressure. So basically, kinetic molecular theory helps explain that. Yes, as you decrease the volume, the pressure can increase, but it's if the temperature remains constant, and it's because of the fact that those number of collisions with the surrounding surfaces are increasing. Now think of Charles's law. So we know Charles's law is the relationship between the volume and temperature at constant pressure and number of particles. So if I increase my volume, I'm increasing my temperature. So at a constant pressure and constant number of particles, the volume of a gas is proportional to its temperature. According to kinetic molecular theory, we know that if we increase the temperature of a gas, we're basically increasing its speed, right? We're giving it more energy to then have the particles speed up. And thus, the particles will increase in the way that they move. And since greater kinetic energy results in more frequent collisions and more force per collisions, the pressure of the gas, if it's held constant, will then keep the volume from spreading up. And if it's not, if the volume is held constant, the pressure will increase. So that's basically the other Gay-Lussac's law. So basically, if the pressure is held constant, the speed of you can't really see this because this is red, but the particles having more collisions will force this balloon to expand. So it forces the volume to increase. So the only way for the pressure to be constant here, because you have this increase in energy and this increase in collisions from the temperature becoming higher, is to actually increase the volume. Now, the opposite is that is if the volume was held constant, then it would be an increasing of pressure because there's more collisions. So the greater the volume spreads the collisions out over a greater surface area so that the pressure stays constant. If the volume didn't increase with the increasing in temperature, then you would have an increase in pressure. And for Charles' law, we don't want that. So in order for the pressure to stay constant, the volume has to increase. And then to explain Gay-Lussac's law, the volume would be constant, and that's how the pressure increases. Avogadro's law. Now, Avogadro's law is a relationship between the volume and the number of particles. It states that at a constant temperature and pressure, the volume of a gas is proportional to the number of particles. According to kinetic molecular theory, when we increase the number of particles in a sample, we have a bunch more particles, and what are they going to do? If we have more particles, there's going to be more collisions with the surface, with each other. So if there's more collisions between these particles, they're going to force a greater volume. The greater number of collisions results in a greater overall force on the surrounding surfaces. Now again, if we want to keep the pressure constant, we have to expand the space that these particles are in, which means you actually have to increase the volume. Dalton's law. Dalton's law of partial pressure says that the total pressure of a solution is equal to the sum of the partial pressures of that mixture. And that could be however many there are. Now, according to Dalton's law, we know that the components in a gas mixture act identical and independently of one another. So they apply a pressure and they have similar behavior, and then they also exert their own independent pressure to the overall pressure of that mixture that they're in. According to molecular theory, kinetic molecular theory, the particles are negligible in size and they don't interact. That's where that billiard ball example comes in, right? So we have our A, which will hit B, to then have B move further. What we don't have is that A hits B to become AB. They do not collide together, right? They do not interact. The only property that distinguishes one type of particle from another, we know, is its mass. However, even particles of different masses can have the same average kinetic energy at a given temperature. So they can exert the same force upon collisions with the surface. So adding components to a gas mixture, even different kinds of gases, has the same effect as simply adding more particles. This is how that Dalton's law is proven, because they can be made up of different things, different masses, but they can exert the same kind of energy, which then helps explain that the partial pressures of all components sum up to the overall pressure, because it doesn't necessarily matter on their mass. They're going to exert a pressure even if they're different kinds of gases, which will then just be the sum of the total pressure of the mixture. So then the total pressure of the collisions is therefore the sum due to the same average kinetic energy. So even though every single particle behaves itself, they're negligible in size, since they don't interact, each particle consists of its own collisions, and each particle's collision has its own average kinetic energy. The sum of the pressure is then the sum of all of the collision, proving Dalton's law. So before we move on exactly to temperature and molecular velocities, I want to just explain a little bit more about, I'm going to use my little blank space here, the kinetic molecular theory and the ideal gas law. So we know that we've just kind of talked about how each gas law conceptually follows the kinetic molecular theory. So again, three things that you're mainly thinking of: the negligible size, the collisions between themselves and the surfaces they're around, and the fact that when you increase the temperature, you're basically increasing the speed. And so how different things are held constant with those three rules is how those gas laws are explained through kinetic molecular theory. We can also derive the ideal gas law from the postulates of the kinetic molecular theory. The kinetic molecular theory is basically a quantitative model that implies the ideal gas law. So the pressure on a wall of a container occupied by particles in constant motion is the total force on the wall, basically due to its collision divided by the area. So if we just explain pressure is the total force divided by area. We know that force is associated with an individual collision mass times acceleration of a particle. And the acceleration of each collision is a change in velocity divided by the amount of time. So I know force is equal to mass times acceleration, and then I know that acceleration is equal to the change in velocity divided by the amount of time. So then I can implement that into my pressure, and I can say that, actually no, implement my pressure yet. I can still say that then my force is therefore equal to my mass times my change in velocity over change of time. Now, if a particle collides elastically, remember these are elastic collisions because they don't come together, they're just constantly hitting off of each other and the walls that they're in. We know that a particle, it bounces off the wall with no loss of energy. Energy is only transferred. For a straight line collision, the change in velocity is 2 times the change in velocity. So the particle's velocity was before the collision, and then the particle's velocity after. That's what the change comes in, right? So it would be whatever it was after minus whatever it was before, because the speed changes. So you think of how ball A hits ball B. At first, A was faster and B was slower, but then B became faster and A was slower, so we're thinking of the change. So then we can think of writing this as force is equal to m times 2v over the time interval. So the total number of collisions in that time interval on a wall of the surface area is proportional to the number of particles that can reach the wall in this time interval. So all particles within a distance of the wall. These particles occupy volume given by the speed, time, and area. So we can then think of the fact that the number of collisions can be equal to the particles that are within. So we can think of the volume and area times the number of particles within that volume, so it's density. So then we can go back to thinking that our total force will be the force of the collisions and number of collisions. So the total force of our substance will equal the force of all the collisions and then the number of collisions that you have in total. Since we already know that pressure is equal to the force total over area, you would then just plug in everything that you have. So you would say, okay, well, I know for this, I have that the mass times the change in volume over the time interval multiplied by volume and time interval, area, and particles over volume, which then gives me that my pressure total is equal to what I got for my force over what I have for my area, which then basically gives us out to the ideal gas, thinking that it's pressure, which will be related to the temperature, number of particles over volume. And then to help assign the direct proportionality and units, we came up with the ideal gas law. So this just shows you how all the different parts are related, knowing that pressure is the force over the area, force is mass and acceleration is specifically the change of volume over time. And then we like to think, okay, well, what about the number of collisions? The total number of collisions in the time interval on the wall of a surface area is proportional to the number of particles that can reach the wall in this time area or time interval. So basically, it depends on the space to figure out how much time it takes for those particles to reach that space. So we define it as volume times that time interval and its area. And their total number is equal to its volume multiplied by the density of the particles, which is N over V. So then the total force on the wall is equal to the force per collision multiplied by the number of collisions. And the pressure of the wall is equal to the force divided by its surface area of the wall. So then we can notice how there's different little gas laws implemented and then rearranging to then find ideal gas law. So in other words, the kinetic molecular theory, which is a model for how gases behave, predicts the behavior that is consistent with our observation and measurement of gases. In kinetic molecular theory, we have a model for what a gas is like. Although the model isn't perfect, it predicts a great deal of behavior of different gases. It's a good approximation of what gases are actually like. Okay, so thinking of temperature and molecular velocities. So again, according to kinetic molecular theory, particles of different masses have the same average kinetic energy at a given temperature. So we know that kinetic energy depends on mass and velocity. 1/2 mass velocity squared. The only way for particles of different masses to have the same kinetic energy, so we know